Hello, today we're going to be talking about calculating the derivative of a function. So previously we've gathered that if you zoom into a curve, eventually a point will look like a straight line around it, which is the derivative. Oops. So if we could somehow calculate the gradient of this line, then that'll be the derivative. But it's a bit hard to calculate something by saying, oh, we just infinitely zoom in, and then that's the point. So another way of looking at it is if we have another point, and then take the gradient of this, you can see that this point right now is not very close to the curve, and definitely not close to what the tangent should be. But as you slowly zoom in, just like how you'd be zooming into the graph, the tangent will slowly approach the curve. And the idea is that if you zoom in infinitely close, if you keep on zooming in, you can see that it's still not at 0. But now if you zoom out, it's pretty much there. And this is basically how you find the tangent. So if we go to our thing, the idea of having our point over here and then our second point, and finding this gradient over here, well, this gradient is basically a right angle triangle. This will be somewhere on the xy plane, so if we have this point as x, and then the point, let's just call this x plus s, for some value s that is like incremented along the x-axis. And then similarly for the y, well, y is a function of x, so the y at this point of x is going to be f of x. Similarly, the y at this top point is going to be the function of this. So this is going to be f x plus s. Now, if you recall, the gradient is y2 minus y1 over x2 minus x1. And now we can plug these 4 values in. So y2 in this case is f x plus s, and then y1 is the regular fx over. Now x2 minus x1, in this case this is x plus s minus x, which is this, and these will cancel out to leave only s. So your function, well, the gradient will be of this equation for this x plus s. And in our example over here, s, we want it to slowly approach 0, but we don't know how much, so we'll just keep it as s for now. But the idea is that we want this to become like x plus 0.1 divided by 0.1, and then for an even closer one, 0.01, and then 0.01, etc., etc. Now, as we get closer to 0, we'll never actually reach 0, because if we did, then this would be dividing by 0, which is an error. But we just want s to approach 0 and to get infinitely close, which is basically the basis of calculus for integrals or derivatives. We're just dealing with infinitely close values or infinitely far values. But for now, we'll just treat this as a letter S. So this over here, this is the first principle, and this can be used to calculate derivatives. So, for example, if you wanted to find the derivative of x squared. So this means your function fx is x squared. So plugging this into the first principle equation, you'll have you'll have your equation. Paste. Right. Now, for our fx, we can plug in x squared. So this turns into x plus s squared minus x squared, because that's just fx, and then over s. Now we're still dividing by 0, which is the main problem. So what we want is to be able to eliminate this s, and we can do this by working out. You'll see how the s will cancel out. So working with this, if we expand the bracket, this becomes x squared plus 2xs plus s squared minus x squared over s. Now we have an x squared and an x squared, so these can cancel out, leaving us with 2xs plus s squared over s. And now somehow magically every component has a factor of s. So now this means we can cancel out an s from each thing, which gives us 2x plus s. So we have this equation right here, and as we said before, we want s to approach 0 so that this gradient becomes infinitely small and will become the tangent point. So basically what we do here is that we just take this s and then we plug 0 into it. And what we're left with is 2x. And so now we can say that the derivative of x squared equals 2x by first principle. Now if you wanted to repeat this and take the derivative of 2x squared, it'll basically be the same thing, but over here instead of x squared plus 2xs, this will just be 2x squared, this will be 4xs, this will also be 2x squared, and they'll both cancel out anyways, and then this will be cancel 4, leaving you with 4x as your answer. And this is the same answer you'll get from just the regular method of deriving, which is just 2x, and then this is going to be 2 minus 1, and then you take this and then multiply it over here, or whatever. So it becomes 4x to the power of 1, which is the same as 4x, which will yield the same result. This holds true for any polynomial. So we can do one more example with x cubed. After that, it gets a bit tedious from expanding all those brackets, but finding the derivative of this will be f. Yeah, so applying first principle function, we will get x plus s cubed minus x cubed over s. Now, expanding x cubed, that's just x squared plus 2xs plus s squared multiplied again by x plus s. So that gives you x cubed plus 2x squared s plus x s squared, and then plus another sx squared plus 2x s squared plus s cubed. And then simplifying or collecting all the terms of this, 3x squared s plus 3x s squared plus s cubed. So let's take this and then plug it back into the equation. So now we have x cubed plus 3x squared s plus 3x s squared plus s cubed minus x cubed taken from here all over s. And same stuff as before, we have the x cubed term that we can cancel out. And then lo and behold, each of these has an s term. So now we can cancel out that divided by s, which is the main problem because we don't want to divide by 0, and then we get 3x squared s plus 3x squared plus 3xs plus x squared. And now we want s to approach 0. So this will become 3x. Oh, this is supposed to be an s squared. This becomes 3 times x times 0, which becomes 0. This will be 0 squared, which is also 0. And what you're left with is 3x squared. So therefore, the derivative with respect to x of x cubed is 3x squared. So the way that these powers work for like x4, x5, etc. You'll learn this in advanced higher if you take this, but basically it follows this thing called the Pascal's triangle. So you'll notice with the x cubed example we have 1x cubed, 3x squared, 3xs squared, and then 1s cubed. And then with the regular. With the x squared one, it's just x squared plus 2x s plus s squared. So this holds true for any. So for example, so this is, that is an awfully thin pen. That's a bit better. So this is the x squared, this is x cubed. So it carries on for x4, x5, x6. So if you are expanding x plus s5, it would become x5, 5x4 s, 10x3 s squared, etc., etc., etc. But most of that doesn't matter, because the only thing that really matters is that this term is the same as this term, because this is the term that would become 5x4s, and then since it's only got one s, this will get cancelled out in that division by s, because any of these other ones, this will be s squared, s cubed, s power 4, s power 5, and then all this will become 0 when you take the what's called the limit. So what matters is that this is 5, and then this goes 1, 2, 3, 4, 5, etc., etc., which is basically what we're seeing here, where x squared becomes 2x, and then x cubed becomes 3x squared. It's basically just an expansion of the binomial theorem, which is the thing with Pascal's triangle. That's basically how to calculate derivatives with the first principle. Of course, in your exam, you're not actually going to be doing this. You'll just be doing x squared equals 2x. But if you wanted to calculate it the long way, this is how it's done. And that's showing how this isn't just a number just taken out of thin air. 5x4 is 20x3. It's not just a random number. It's basically the equation of a gradient that is slowly approaching 0 from some point, like so. Now this works for trigonometric functions as well, like sine x, cos x, but that is a lot more complicated, so just take that one at face value. But for polynomials, that's how you calculate a derivative the long way.